pleased to have Xincheng Zhang, who's going to speak about TASEP in app space.
Okay, so hello guys. So this is based on recent work I just finished. So the paper I posted yesterday, so it should be on archive like later today. Okay, so today I'm going to present you with a formula for the half space TASEP. Huh? No. Yeah, I have a good sleep. Yeah, okay. So the plan for today is that I'm going to present you with the TASEP, the formula for the half space TASEP, starting with general deterministic initial condition. And then I will try to convince you as much as possible that the formula is correct without the proof. Okay, and then that's the plan. Okay, so the model is the no. The paper has rigorous proof. Okay, but I can't cover them in the talk. So the half space TASEP is that is a particle system on the positive integer side, and they're trying to jump to the right hand side with rate 1 if there's no particle in the way, and then there is a reservoir of infinite number of particles, so they will try to jump into the positive line with rate alpha. Okay, so in this talk we are going to exclusively like using the height function representation. So the dynamic reflected on height function is that every local peak at rate will like switch to a local max will switch to a local mean at rate 1, and for the peak at the origin, so this is considered as a peak. You just look at it from the right hand side, and this will switch to the local mean with rate alpha. So all the box here will have rate alpha, and the box here have rate 1. And this is the model. Okay, so the object we're going to study is the probability that you're starting from some initial configuration. And at time t, it is staying below another configuration. So this is the probability we're going to study. So before we start, let me give you some literature review. So the study of the half space problem back to 2000 in Baker and Rings. So they studied the symmetrized longest increasing subsequence, so which is kind of like a Poissonized LPP in half space. So in this paper, they identified 1-point distribution. So this is basically a Poisson LPP, starting with narrow wedge initial condition. And in this paper, they identified the different phase transition of the 1-point distribution depending on alpha. So when alpha is greater than 1/2, you see the GSE distribution. And alpha equal to 1/2, you see the GOE distribution. And alpha less than 1/2, you see the Gaussian. So this is one of the important features of the half space models in the KPC universality class. And then so the model and Imamura at 04 have the PNG. But PNG is basically a Poisson version of OPP. So starting from narrow wedge and the multi-point distribution. And then more recently, Bike, Parakan, Corwin, Sudan. So they have two papers, like they study the LPP, the geometric LPP and the exponential LPP. But that basically corresponds to TASEP with narrow wedge initial condition. Oh, sorry, TASEP narrow wedge. So in this paper, they like build up the crossover kernel, which interpolates between like different regime. And then by Battia, Harari, Orcelli are 20 and 21. So they also studied the stationary LPP. So which is a version of like TASEP starting from product Bernoulli measure. Okay, so these are the previous work. Okay, but there are more work like recently about half space models, but I can't cover them all. Okay. Okay, so now back to the question. So we're going to develop some notation for the height function. Okay, so we're going to put some assumptions on the initial configuration. So we will assume that the initial configuration has finite number of peaks. So by peaks, I mean the local max. So in this picture, there are 1, 2, 3 peaks. And we assume that the function goes to -infinity at infinity. So if you have this assumption, the configuration is uniquely determined by the place of the peak and the height of the peak. So we will use notation to denote the peaks, to denote the height function. And then similarly for the final configuration, we assume that there are a finite number of troves. So troves means local mean. And we assume that the function goes to plus infinity at infinity. So similarly, it is identified with the place of the trove and the height of the trove. So we use the curly brackets to denote them. Okay, so these two notation completely determine the configuration. So we basically study the probability that you're starting from some initial peak configuration, and at time t, is this staying below the trove configuration. Okay, so notice that with finite number of troves, this is basically the M point distribution, because a configuration staying completely below some trove configuration, if and only if at the trove you are staying below. So this is basically asking the M multi-point distribution of the height function. Okay. Okay, so but this is not what we are going to use. We are going to do one more change of variable. So what we want to record in the relative position. So now we think of each configuration is flipped from some peak. So for example, for the blue one, you think of there's a peak here. And then you can see that you can think of this blue configuration is got flipped from this peak configuration. Right, okay, so this is what we call the primordial peak. So thank Jeremy who gave the name to the peak. Okay, so this is what we call primordial peak. And then you can see that as long as we know the primordial peak, we can identify the height function using the primordial peak and the relative position here. So what does that mean? So we define ui to be the up step from xi minus 1 to xi. And the di is the down step. So basically, from this, so this is like down d1 with 2 steps. So this is d1, and this is up 1, and up 1 is equal to 1, and then down 3 steps. So this is d2 equal to 3, and then this is up 2 equal to 1. So these set of variables recording the relative position of between the peaks. And then we define 2 more variables. So u is the sum of ui, and the d to be the sum of di. So this is the distance from the primordial peak to x1, and this is the distance from the primordial peak to xn. So you can see that if you pull out the u1 to this side, this is u1 here and the u2 here. So this side is basically the sum of ui's. And this distance is exactly the distance from the primordial peak to the first peak. And then for di, so you push all this to here. So this part is d, which is the distance from the primordial peak to the last peak. So that's the meaning for u and d. Any questions? Okay, right. So then we need 2 more variables. Okay, so we don't really want the primordial peak. What if xy will always be a peak? So we just if the peak is not at 0, you just change it to another. Yeah. Okay, so we need to define 2 more variables. So which we call AOPQ. Okay, so this will be the distance from the primordial peak to left of cone CPQ, and the left and the right PQ will be the distance from the primordial peak to the right of cone PQ. Okay, so I'm going to tell you what is the cone mean. So for example, let's take example that PQ equal to 0, 0. So that's just the absolute value function here. So this is the cone. And you can like, if you shift the coordinate, you just shift the cone. And then L is the distance from the primordial peak to the left side. So this is L. And this is right. This is R.
Are you finding two functions of P and Q?
Yes, right. So when you're trying to specify like the L and the right, you need to specify what is the cone you are respecting to. Okay, so PQ is some prescribed coordinate. They will be used like later. So you can see that you want to kind of specify like, so you can see that there is also a primordial peak from the end configuration. And you're kind of you want to use L and R to specify the relative position of the primordial peak of the initial and the primordial peak of the final. So that's why you want this P and Q. It's kind of like denoting the relative position of them. Okay, I will explain PQ, like they do appear and I'll re-explain them. Okay, so after this, we can define our product. So we can define a kernel.
When you say this, sign distance.
No, it's just the number of wedges, number of wedges.
So always non-negative.
Yeah. No, it can be negative.
Can be negative.
Yes.
So it's not a distance. Sign distance.
Right. You're right.
Linear function.
Yes. It's just a basically like linear change of variables. Yes. And you can see all these variables like U and D are some like linear combination of X and Y's. I just didn't write them down here. Okay, so now you can define the following operator. So now if I specify a cone and also a peak configuration, you can define the following operator. So W is defined to be B star inverse A star right minus left I minus AU indicator function T W1, 2. Oh, sorry. This is AD and A star L minus left and B star. Okay, sorry, I should move. Okay, so I will tell you what is A. So all these A and B are some small differential operators. So A is equal to 1 minus 2 partial. And the A star is equal to 1 plus 2 partial. So this is really the adjoint of the A. But I put the star in the subscript because the superscript is for powers. And then B is equal to 2 alpha minus 1 minus 2 partial, and B star is 2 alpha 1 minus 1 plus 2 partial. And if you have a inverse, if you have a negative power, for example, like this is a negative power, then it will be the inverse operator. And I will tell you in a second what does that mean.
So tell us what delta.
There are okay, partial just means the differential operator.
So at least two possibilities.
Okay, right, that's right. Okay. So it turns out that it doesn't matter.
Okay.
No, yes, so the partial, so
It's
it's just like you take a derivative on the X variable. So if you d f x is equal to f prime x.
these are going to be discrete functions.
No, this will be on continuous function. Okay, so now I can state the main theorem. So let me state the main theorem here. Oh, right, sorry. So Wi plus 1 is equal to A minus A is up K star minus di. Okay, maybe I can tell. Okay, I should also tell you what is the left minus right mean. Okay, so in a second. So all these variables have a clear meaning on the pictures. Okay, so I can state the main theorem. Okay, so the theorem is, so the probability that you're starting from a peak configuration and you go less than a trough configuration is equal to square root of determinant I minus K as SCA means it is a scalar kernel act on L to R. And the KS is equal to SLL11. So this is an operator parameterized by 4 variables. K initial, SLL11, K final. So L is equal to Rn plus Xn minus Sn plus Ym over 2. And the K initial is equal to Wi plus partial inverse Wi star partial minus W inverse partial I star partial Wi. And then K final is all the, okay, let me just write that down. K final plus D inverse. It's the same. Okay, but then what is this Wi? So Wi is the operator W there. And it is parameterized by the cone at Sm minus Ym. Okay, I will explain what this means on the graph in a second. X R. And the W final is the cone at minus Xn minus Rn and the trough configuration. But you flip the trough, and then you can think of this as a peak configuration. So that's why this is a minus S. Okay, and then what is S? So the S operator here, S P Q I J is a contour integral. So it's a kernel given by the following. X plus Y greater than or equal to 0. So this is a normal object which appear in the KBC class. So the 4 parameters IJ, PQ basically indicating the index here, the power here. And IJ will only be like 1 or minus 1 or 0 because they are the power on alpha. So IJ will either be like minus 1, 0, or 1. And the contour here, including the pole at 1/2 and 2 alpha minus 1/2. So including pole at 1/2 and the 2 alpha minus 1/2. That's the only 2 poles in the formula. Yes, question. Yeah. Okay, I will explain. In a the way it is written, it is not, because there's some differential operators in the end. But I will show how you can make sense of it in a second. Oh, okay. Right. So so to define a W operator, you need to specify the peak configuration, which like define all these U and UD and UIDI. And you need the P and Q to define your L and right, left and right variable. So the cone is kind of denoting to tells you what is L on the right. So that's why you need these two extra parameters. Okay, and then I will explain this on the graph. So
everything is not.
yes, exactly. Yeah.
It's explanation.
Yeah.
In terms of definition, you have everything in the board. That's the cone, which is over there.
Right.
And that divides the W.
Yes.
And the W.
Yeah. But the well-defined is I need to explain this. Little r. Okay. Okay. So what is this? What does this cone mean? Okay. So you should think of this as like parameterized by the peak and respect to some cone. So the way you generalize this, the way you like generate all these parameters is like you look at the initial configuration, you find your peak, and then you also find the peak for the final configuration, and then you extend this point to here. So this is the 0 SM minus YM. So you want to generate your configuration with respect to this point. So this is the cone. So this is the cone when you're defining like the W initial. And then in order to define the W final, you find out what is the primordial peak for the initial configuration. And then you extend this to 0. So this point here is minus XN minus RN. So the reason you want to look at here rather than here, because you need to know like how far it is from the origin. You don't have the horizontal shift invariance in half-space models. So that's why you and then the left minus right, which find okay, so the left minus right, L minus R is just this part, the distance here. So this is the distance L minus R. It's how far you are away from the origin. And then this distance is L minus R prime. So R prime is denoting all the variables for the final configuration. And then there is a feature is that, so what is this L? So it turns out that WI and WF, they share the same L. That's the box where they live in. So you can see that, okay, so you can see that L is the distance for this big box. Okay, maybe I'm so you should think of like all the configuration actually live in this green box. And the L here, which is a common L shared by W initial and W final, is this thing. Any questions?
Where is R defined? Sorry.
R defined. Okay, R is here. Yeah, so R is the distance from the primordial peak to the right of the cone.
That has subscripts.
Yeah, P and Q. So when you define the WI initial here, the P and Q is 0 and SM minus 1M. And the SM 1M is basically the point here. Oh, right. So time, okay, right. So time is here. Time is in W.
This should be RI and
RI.
The R prime is like RF.
Right, exactly. Okay. Yeah, that's right. Okay. This is all the variables for the final, and this is all the variables for the initial. But then the left will be the same. That left, yeah. Initial. Okay, right. So T is in the W.
You didn't say.
Yeah, what, yeah.
Okay, sorry. So yes. So 1 bar T is the indicator function that x less than or equal to t. Yeah. And then we use the notation also like this t. So if you put t in the bottom, it just means that it is from x greater than or equal greater than t. So bar means the endpoint is included. And whether it's up and down means like you go to plus infinity or minus infinity.
So can if I set t equals 0, can I see this formula simplifying easily?
Yeah. Yes.
I guess the probability should always be
0 or 1.
Should always be 0 or 1.
Yes.
And is that clear?
Not clear, but it's true.
Okay.
Yeah, that's one point, one component of the proof that my formula is correct. Okay, I will explain. Okay, wait. Okay, right. I need to say one more thing. Okay, so in WI, all the indicators are T, and in W final, all the indicators are 0. So I should say that. So the indicator T becomes indicator 0 in the final configuration. So you don't need the T in the W final. Okay. So even this is not okay. Now let me tell you what does all this BB inverse mean. So B inverse, you should think of B inverse is okay. Wait a second. Is there any questions about the formula? Okay, right. So now I'm telling you what is the BB inverse. So B inverse is an integral operator with the following kernel. And the B star is basically Y and X switch positions. So this is for alpha greater than 0, alpha not equal to 1/2. And then for alpha equal to 1/2, B inverse is equal to, so while alpha is equal to 1/2, basically B is just the partial operator, right? Because this is 0. So B inverse is and B star inverse is
This is like integral kernel operator. And then it's an inverse of the derivative with respect to some.
yes.
Oh, I see, with respect to just the back measures.
Yes. So yeah, so if all these AB with a negative power, that's an integral operator, and with positive power, that's a differential operator. Okay, then there's the one tricky thing here. So if you look at this operator, when alpha is greater than 1/2, this is positive. So this is positive, and the y is unbounded above. So as y goes to infinity, you have the correct decay. But when alpha is less than 1/2, you can see that it is actually the function not even decay, right? It's increasing as y goes to infinity. So it's not well defined yet. Okay, so the definition is that, but we still want to adopt this definition. So this is kind of a non-physical Green's function. Okay, but then what if, like in the case that alpha less than 1/2, you will have some B inverse composed with B star inverse. So the definition, so you should think of that in that case, you should think of like B inverse with B star inverse as one object. And it is defined to be, okay, I will not write down the formula, but I will tell you how you think about this. So it is just, so the normal composition of B star inverse and B inverse and B star inverse is just integration, right? So you integrate these two things. And the E2 alpha minus 1/2 Z minus Y. And dy is from max of X and Z to infinity. But this thing is divergent when alpha is less than 1/2. And the correct definition is just you change this infinity to minus infinity. No, this is really correct. This is really what you want. And then it has the amazing property that, so this have the property that although like you don't like operator don't compose in this way, But the point is that you still have the kind of the operator property that B hit on this object is equal to B star inverse. And B star hit on this whole you should think of this as one object is equal to B inverse. So that's the key property we want. And all these operators still like commute with them. Okay, so that basically make the everything well defined in the operator. But then there are two natural questions, right? First is that, so I'm taking a square root of determinants, whether it is positive. And another question is like, whether the kernel is like even an integral kernel, because there are a lot of partial operators. So in this W, right, there are a lot of ill-defined objects. So you have A and D, the AU and AD on the two sides are pure differential operators, and they are hitting some indicator function. So how to make sense of it as an integral kernel? Okay, so in order to make sense of them, let's first address the first question. So let me just state the Fabian version of the kernel. So there is, you can rewrite this kernel into a Fabian version, and then the kernel will be anti-symmetric. And you will know that the determinant must be positive. So the Fabian version. So the same object is equal to the Freidom-Fabian of J plus JK on L2R. And then it is, if you don't know what is the Freidom-Fabian, it's just the square root of determinant of 2 by 2 matrix. And now it is on L2R times L2R. Okay, and then K is a matrix. Okay, so this is the Fabian version. It's written in a 2 by 2 matrix kernel. So all S here are SLL11, same as above. Yeah. So you don't need to know J, you just need to know this is the square root of determinant. But J is, yeah. Okay, so the theory is that if the kernel JK here is anti-symmetric, then this determinant is positive, and you can take a square root, no problem. Okay, but but then it is not very obvious that this kernel is anti-symmetric yet, right? Because so this is the way of the form of the kernel that it is most symmetric in initial and end configuration. But then in order to see it is anti-symmetric, you break the last matrix into 4 pieces. So this matrix is just the multiplication of just break it into like simpler components. And then you move using the property that determinants I minus AB equal to determinant I minus BA. You move these two matrices into the front. And then it's very easy to check. J minus this matrix is anti-symmetric.
What? What does the determinant identity have to do whether a matrix is antisymmetric or not?
So it might be some, if it is written in some form.
No determinants involved.
Yes, but like it might be in some form, it's just difficult to check is antisymmetric.
That's not what he said. He said that this is antisymmetric.
Oh, no, wait. No, it is possible that
The determinant is equal. I think there's a step, which is that it's not maybe not antisymmetric, but it's equal to the determinant of something that's antisymmetric.
I guess so. Yeah. That's what you mean.
I'm not sure if this matrix is antisymmetric, but it's at least not easy to check. Yeah, but then if you use the identity and move this thing to the front, then it's
You
easy.
get the new matrix. That's
Multiplied by J will be antisymmetric. Yes, and it's easy to check. Okay, so this answers the question that like we can take a square root on the determinant because you can show that that thing is just some transformation of this matrix kernel, and then it will be positive because it's a determinant of like antisymmetric matrix, like a Parthian of an antisymmetric kernel. Okay, so the second question is, right, we need to how about all these differential operators here? Okay, so we are going to study these operators more closely. Okay, so let me write. Yeah.
So the definition of S, like the PQIJ, like what are you integrating over? Like what's the integration variable?
Right, so integration, oh, sorry, yeah, integration variable is dw. Yeah, sorry. And this is basically the residue calculus. There's nothing, like you can compute this explicitly. This is just the residue at 1/2 plus the residue at 2 alpha 1 minus 1/2.
This stuff is not with the operator.
Right. Yeah, oh, right, sorry. Yeah, okay, so, okay. So now I'm going to explain how to make sense of the operator as an integral kernel, and I will show its in trace class. Okay, so this has something to do with the manipulation of this W kernel. So this W kernel is the kind of the singular object. You have, so all the differential operators are here, a to the power of u, a to the power of d, and a to the power of left minus right. And then they're hitting indicator functions from the right-hand side and left-hand side. And then if you look at this matrix, on the other side, they are hitting S. So S is an object with some indicator function. So it's kind of like you have a differential operators surrounded by like a lot of indicators, so which is kind of singular. But okay, so let me. Okay, so if you look at the middle of the W, let me show you some manipulation. So the middle of the W is I minus AU. Okay, so the following operation kind of like illustrates the spirit of all the like the proof in my proofs. So notice that if the indicator function here are not present, then like this have the same number of like a, oh sorry, this is a star. This is a star. You have the same number of a and a star on the two sides with the inside. So inside is like, because if you look at definition of Wij here, it's just summing over ui's, which is equal to a to the power the power here. And then if you're summing over a star, it's summing over di, which cancel with the last d. So if the indicator functions here are not present, so they will just cancel. Well, you get identity, and you get 0. The whole thing becomes 0. Okay, so the manipulation we want to do is to get all these differential operators across the indicator. So let me do one step of the calculation. So this thing is equal to I minus a u. So we move u1 number of a across indicator. Plus, okay, so dot I just means doesn't matter in the end. Plus commutators. So commutators is just like you across the indicator, you get some delta function. And then you can see that this thing, AU1 will cancel. W12 is A minus U1, A minus D1. So they cancel. it will cancel out all the, oh, sorry, A star. Yeah, A star D1. So it will cancel all the A part in W12. So what's left in the first component is just A star minus D1 indicator T. But then the thing is that if you have an A star operator surrounded by indicator T and indicator T, the second indicator T can be dropped. The reason is that if you look at the star operator, it is supported on X greater than or equal to Y. So the A star, so this operator, A star minus D1 here, is supported on X greater than or equal to Y. So if you know X is less than or equal to T, that guarantees the second variable will be less than or equal to T. So the point is that after you cancel out all the A operator in W12, when there's only A star left, you can remove this indicator T. So this is just equal to this is not here. And then you can bring more A star into it to cancel the, okay, then the term becomes W23. And then you can bring more A into it to cancel out with the A operator in W. Okay, so eventually, okay, you do this operation. You want to bring all the AU across this indicator T and all the AD across A star D across this indicator T. So basically, this whole thing, you should think of this as just sum over AU minus I, delta T. So delta T is the commutator terms. Whenever you have a differential operator across the indicator function, you have delta T. And then you have some operator in the middle. It doesn't matter what this thing is. This is the integral operator. Delta T. A D minus J. So this is a sum over all the commutators you have when you bring AU and A star D into the indicators. And then in the end, when you have all the AU and AD inside, they just cancel inside. The inside there's nothing left. What you have is in one minus. So you have plus identity minus the indicator function. And this is just like indicator T. So the whole point is that this operator W is just this indicator T plus like finite number of rank 1 operators. So this is rank 1. Right? Because this is because you have delta T hitting an integral kernel. And then this is a rank 1 operator. So this is a finite rank object plus indicator T. Okay, you might want to ask, okay, so now you have, so this some like indicator function, there are still some like differential operators left on two sides. The whole point is that whenever you have a delta function on one side, this then can go through into the indicator function and hit S. So there will be no problem on the other side. Okay, that's very quick. So the point is that if you have indicator function on one side, then for example here, on the other side, when you hit a S, this indicator function, it doesn't matter anymore, and the partial operators can directly hit the contour integral inside, and this is like a smooth object, so there's no problem. So the conclusion is that so then it is not difficult to believe that like operator like S indicator TS is trace class, right? Because like these S are just like common stuff in the KBC models. So the conclusion is that the kernel is something in this form plus like finite rank perturbations. And this is in trace class. So the whole kernel is in trace class. And because you can make all the differential operators hit S or bring inside. So this is really an explicit integral kernel. So you can, okay, so in a simple case, you can really write the kernel out. So, okay, so there comes the reality check. So in a very simple case. Yeah.
you only have 5 minutes.
Right.
Maybe you should, like, I think many people are wondering, how do you know this form is rapid works?
Oh, okay, right. Okay, sure. But let me just finish this. Okay, so this is what this is part of the reality check. Okay, so if you start the initial configuration from here, this is our initial configuration, and then you ask the probability at time t is staying below the blue curve. So the probability is just sum of like exponential random variable plus the maximum of exponential alpha and exponential 1 plus exponential 1. So you can compute the CDF explicitly. And then you can write out the kernel. You can write out the integral kernel explicitly and compute its eigenvalues. The product of eigenvalues really is the CDF of this model. So that's one reality check. Okay. Right. Okay. So then basically this finished the well-posedness. Okay. It's a integral kernel, it's trace cast, and everything is explicit and well-defined. Okay, so how I'm going to prove this is correct? So prove this is correct by so the proof idea is that you prove like the determinant satisfies the Kolmogorov equation. So which is dt minus the generator acts on the square root of determinant is equal to 0. And then you check initial configuration. So as t goes to 0, so this will be either 0 or 1, depends on the configurations. So this should be the indicator that whether your h init, whether your x is staying below ys. So this is checking the correct initial condition. And then last thing you prove this set of equation is unique. And then these three proves that. So because the half-space TASEP formula must satisfy 1 and 2. And if it is unique, then my formula, it must be the formula for half-space TASEP. Okay, so that's the proof. Okay, and then where does the formula comes from? So this is by guess and check. So okay, so how do you guess the formula? So from the BBCS 18, actually you have a lot of information. So they have the multi-point. So they have the multi-point to like narrow wedge, right? So that's what they done in BBCS 18. But Baik, Barakan, Corwin, and Sudan. Okay, so if you can do multi-point, that's basically like general and configuration. And then there's one point in the TASEP is that the skew time reversibility, skew time reversal invariance. So it should be symmetric in the initial and final configuration in the sense that the time you flip from the blue configuration go below orange should be equal to that you start to flip the orange one and go above blue, because that will all be equal to the last patched value in this region. So that indicates your formula should be symmetric in the initial and configuration. Okay, then in quick word, the first three matrix is somehow already not exactly, but this is basically BBCS formula in rough sense. So these three components, the first three matrix is a path integral version of the kernel in BBCS 18. Okay, and then you just copy this, copy your initial thing to the final, and it can work because it should be symmetric, right? Okay, that's how I get formula, and I guess. Okay, so there were. I guess I will stop here. Yeah, and if I, yeah.
Questions? But
So you're saying these first two, they just see that what the BBCS has for their narrow wedge half space, and then you want to make yours CP time reversible, so you got last matrix. Is that what you did?
Roughly, yes. But this is not exactly BBCS. So from BBCS kernel to this kernel, you need to do a path integral transformation. So path integral transformation is basically you change an extended kernel, like a large extended kernel, to a scalar kernel. And then you apply this on the Fathian version, and you will get. But then that step is only formal because some of the operators in the middle of the step is not well defined, but only the operator in the end is actually well defined. Yeah.
Maybe you should say something about the half space.
Okay. Okay. Right. So taking limits to the half space fixed point is like only like 1 hour, 2 hours work. So because no. So this WI, right, is almost a p hit. So this part. Okay, no. After you move out to AU and AD, this middle thing is basically the p hit operator in the limit. And then all these extras go into S, and which give you the STX which is the STX operator. Okay, so basically, very roughly, let me just put this here. So S go to the STX operator. So STX is E1/3 D cube P plus X D square. And the KIs basically goes to P hit. No. All the WIs here. WS go to P hit. And then you have like a P hit plus some star of P hit so all the differential operators remain in the limit. And you have P hit plus D inverse P hit D minus D inverse P hit D P hit. And then you get the limit formula will basically just be this. You're replacing WI with P hit and replacing S with the limiting operators.
these WIs are also hit operators in the discrete setting in some sense.
Yes. Yes. Yes.
This is are they very symmetric ones in symmetric case?
No.
A different kind of fitting operators.
No. Yes, they're different. Yes.
You rewrite the symmetric, the full space formula using this kind.
Yes.
Oh.
And also, okay, there are 3 amazing properties I can cover for this kernel. So
It's also true, but the full space version of this is also true, but may not be the same form.
What does that mean?
It gives you a formula for TASEP in full space.
Yeah.
Which is not necessarily the legal formula. Though of course it spits out the same answer.
As in it may be a different term with the same.
It's plausible that that kernel is just some conjugation of the kernel, but it's
I
not.
see. So when you
not
say
clear
the
at
same,
all.
I mean, the statement, I guess the statement is that you don't know whether it's a conjugation of that kind.
Yeah.
right, and also there's a property that if you move this configuration in the middle of the half space, then you don't see the dynamic from the origin. Then you should get the full space TASEP formula from this, right? So you okay, so that you can just see from here. So the story is that under that scenario, okay, the whole matrix will be the kernel here will reduce to a upper triangular matrix. So the point is that 1 1 1 2 2 1 2 2. So in the case that the configuration don't see the origin, this thing is 0, and 1 1 and 2 2 are basically the kernel for the full space TASEP. So you can get the full space TASEP from the half space TASEP. Your question here.
So I'm assuming like strict reversibility, obviously, like
goes towards the limit, but you lose the symmetry, I guess, of translation invariance. Do you have like, is it the symmetries of this like half space fixed point? Are they sort of all the same except for translation invariance?
I didn't explore that. But you're right, there's no horizontal symmetry, but the rest of the symmetry, vertical, yes, but some other properties I didn't investigate.
Like let's say stuff like that.
Oh, no, I don't think so. No, no, not known, I guess. Yeah, not known.
Is it clear from the formula that this is monotone in alpha?
Okay.
I know the answer to that question.
All right. No. Monotone? No. No, I didn't even think of that way. What do you mean?
Like if you change your parameter alpha, then the probability is monotone.
Yeah, yes.
Another thing, I guess, related question is, can you differentiate the formula in alpha?
Yes, because if you write out, if you think of the sum is the summing over like these boxes, right? You can differentiate in alpha. But then of course my formula representing this probability, then you can differentiate. You can.
But you get, I mean, I guess.
Okay, can you do?
You can do it, but do you get anything?
Oh, then if you directly on the formula, I don't know. I didn't try.
Because this would be like, you can take a derivative in alpha. This is like how much time the geodesic spends on the line, on the vertical.
I see.
Expectation. Yeah, an expectation. But maybe you could use this to like, if you can do this carefully, you can get like a local.
Oh, you'll get a formula, it's just not clear, it's useful for saying.
In principle, you can get a formula for the invariant measure, but I didn't try. Yeah. So this should correspond to one of the non-product Bernoulli invariant measure.
They know
Right, they know, but so the obvious one is the product alpha. The product Bernoulli alpha, but then there is some invariant measure which is not that, but I don't know what it's like how to describe, I guess.
I don't think there's.
No, it is. Product alpha is the invariant measure.
But if you start from narrow wedge, you don't get that, right?
No.
And these are all close to narrow wedge, so these will all go to the same funny invariant measure.
Right. Oh, and one point is that the finite peak condition can be dropped. So yeah, so the point is that if you have some, so for example, in this graph, this last peak is not doing anything to the probability, because the probability you're starting from blue go below orange only depends on these boxes. This is already below, so it will not affect the probability. Right. So but then in the formula, I also like put this into it. So the point is that this whole parameterization with this peak is equal to the parameterization without this peak. So the point is that you can drop out this peak. And you have the kernel reduction. You can also see this reduction in the kernel. So
So one of your initial and final conditions can be infinite.
yeah. One of
But not both.
not both, no. Okay, thank you.
Well, if you just
I mean, I think if you. There's something about differentiating alpha. Okay, I'm not sure what the exact statement is, but something like like when you differentiate as alpha. If you have like an, I don't know how it's gonna operate at the level of CDI. But differentiating an alpha is related to how much time, like if you think of this as LPP, it's related to how much time your geodesic spends on that line. Right? Does that make sense?
Like this LPP, yeah.
So if you think of half space TASEP as a half space exponential LPP with exponential alpha random variables on the vertical lines, then you can like couple all of these together for different alpha just by like multiplying exponential on random variables by alpha. And so then differentiating alpha, your last passage time just changes according to the number of vertices that you pick up along the vertical line. And so, okay, so how this interacts at the level of the CDF is probably a bit funny because it should be like the conditional law of how much time. So you'll get something like the conditional expectation of how much time you spend on the vertical line, given that your LPP value is a certain thing. It's not exactly the local time, but it's related to the local time, right? But the first thing you would try and check is monotonicity.
Yeah.
Which is. But I don't know. None of these things would be so.
I mean, you do know that like trying to check that a lot of these determinants are actually distribution functions is not a simple thing. Right? So.
But you do get monotonicity like official data of this formula, right? That should be.
Sorry?
You get monotonicity like the initial data from this formula, right? Like you increase.
Well, this is monotone in like many things, right? But you can't see it.
So like if you increase like x's, like they should go down, right? Always is that step there,
If you increase X,
right? Right.
It's
True.
true. You mean, is it clear from the triangle formula?
Yeah,
But these things usually aren't true, clear from the
yeah. Okay.
So the local friendly basic was
I don't know. I think so. He's asking like the visiting time to the origin.
What do you want to prove about what?
yeah, and the number of visits.
Yeah, it's kind of in the middle.
I'm not even sure. I think, I don't have anything in mind. I was just, the first thing would be like, it's like how much time you spend there. Okay, so like.
The most I give you a crazy terminal for us.
Yeah, but
Here's how
okay,
much
but
time we spend.
at least we order up to time t, how much time you spend. Like what is the. order?
Yeah, okay, that's the kind of thing you, okay.
So, and the belief is that it should be, I think like the heuristic tells you. Alan was telling me maybe the heuristic tells you that, okay, like on an arbitrary line, the amount of time you. Like in the half space landscape. In the full space landscape, like the Hausdorff dimension of the intersection of a geodesic with a vertical line is like 1/3. But with this weighted line, it should be 2/3.
Oh,
And you should be able to see that.
yeah.
Like that's something
It's
that
plausible, yeah.
it's plausible that you can see. On a PCM X, can you say something like your formula shows that you should have screen time reversibility? So then like, you know, have some initial or have some final data, have two different initial data ordered in X. Because your formula shows it's your skew time, you put the initial data at the same Y. Now your X is ordered, so that's just kind of obvious because like one now we're finding data. Does that make sense?
For what property?
Like you want to show it's monotone X, let's say. But you can say your formula shows that you have skew time reversibility. So you can turn any like question about comparing initial data to like a question of comparing final data.
Yeah.
Or in data, let's say.
That's right.
And so then you start at the same Y, let's say, and now it's just kind of obvious because like your one final data is above the other data. So
Yeah, I mean, you're not using the one.
or but you said that you said the formula, like, does the K matrix there where you have this, does that make it obvious that you have some reversibility from there or no? I guess that's what I was trying to say.
Yeah, I mean, yes, but
You mean the skew time reversibility from the formula?
Yeah, like, is it obvious?
Yeah. So like skew time reversal is obvious from the formula. That's correct.
Yeah, so then you.
But I'm not sure how that's for the
Yes.
rabbit.
You need monotonicity in some parameters.
yeah,
But I mean, you're working from the point where you're trying to prove everything from the formula rather than just knowing that certain things are monotonous.
Sort of in this case, what's the difference?
Like, well, there's lots of things that are monotone, but the question is, can you prove that anything is, okay, so the simple thing that I attempt to prove is monotone is.
fact you didn't prove with the determinant. That's it. Because when you reduce it to something which is obvious, but it's not obvious because it's determinant, it's obvious because it's physics.
I see, I guess I was thinking that if you can show that, like, the determinant is invariant, like switching X and Y.
Yeah.
But that's not. Yeah, I don't. But.
You say.
That's not going correct.
You're reducing it to the fact. Fact.
I see.
So if I can differentiate alpha, then it would be good to know like know something about.
It'll be interesting, I mean, I'd be curious to know.
I guess it's not easy.
It doesn't look like much fun because there's alphas everywhere.
Yeah.
So it's just gonna get extreme of horrible things.
I mean, is it like, when you, I guess you differentiated T, that you don't go with this,
Yes.
so it's much easier.
Yes, because the P is all the indicators.
Yeah,
And then-
yeah, of course.
All of these.
So if you want to differentiate like spectrum function. Well, I don't, it's not even, I don't think. That's like. Yeah, that's the total. Okay, yeah, so you prefer, okay, so the kind of thing, yeah, that'll be like a better thing to do. In some sense, would be. You first take and see that, produce an expectation, and then you differentiate your expectation off of it. Maybe you put it in opposite. But it's not like a, it was just like an offhand. I think it's.
That's a good comment. Minus alpha should be true. Especially through X equals a half. That would be actually something worth checking,
Right.
because X equals a half, their formula changes, right?
Alpha equals 1/4.
Try to take the derivative at X equals a half.
X, I mean alpha.
Alpha equals
Yeah,
half.
yeah, yeah. That's right.
Well, okay, but I mean, the thing you're differentiating. I think you're differentiating.
You know, like, can you write this? It's nice, it's still like.
Yeah, so I mean, you're essentially like, you end up with like, you end up with you should end up with a conditional expectation. See, it would be weird, but you end up with something related to the conditional.
But I didn't hear everyone be trying to. If we can go, like, if we would go on.
I thought it's something like 30 minutes.
I told you that.
I didn't talk about the three good topics like on the.
It was good. It's hard to explain.
But I think like they get it.
Yeah. And, it's fun, like, good night.
Oh, and for the creepy thing.
There's a couple of.
It's kind of, it's not that easy to check.
I know.
Oh,
Yeah, because like it's kind of,
I think some restart time.
No, you can come by and talk to me.
okay, did you? You have some?
I do have some.
I should talk to James right now, and then I
should
Yeah, I'll let you know.
yeah.
Okay, great. I'll see.
Yeah, hopefully we're
I'm
not.
not sure we would go. I'm not sure.
I think like it's still, swimming might still be okay.
Yeah, I think.
I don't know.
Yeah, there's one shipwrecks on the thing.
So it's. Oh, yeah.
Talking here, before we can go, are you setting up first?
There's a group out there that was just talking to me about.
Okay, we can go upstairs.